All right, let's start one of my favorite lessons, optimization. So you might not know it, but if you're good at optimization, you can get paid to do math for a living. It turns out when people want to hire a mathematician, or they're really thinking about using math in business or industry or out to make good in the world, then they're usually asking for what is the fastest way to do this, or what is the least amount of money spent, what is the most number of people that we can help, and those are all optimization type problems. Optimization can be straightforward if you know a little math. It can also be incredibly hard. It can be the kind of thing that will break your computer, it's so complicated, or it can be the kind of thing that it just takes the right model, the right framework to really blow through a problem. So in this section, we'll focus on some of the first steps in using calculus to help with optimization, but it's certainly not the last steps. If it's something you enjoy, you should keep doing. This topic has a bit of a reputation, just like related rates, for being challenging because it's going to ask you to model a situation and then to find a maximum or a minimum in that situation that might have some geometry. It might require you to read a word problem. It might require you to think about relationships. So it's challenging, but for good reasons, and it's challenging for reasons that are exactly what someone might want of you if they were bringing you in for your amazing mathematical abilities. Okay, so the way we're going to do this lesson is just really a series of examples. So here's our first one. You keep sheep. Why not? This is where almost everyone starts, is for some reason this particular problem. So in this problem, you keep sheep and you have 1,600 meters of fencing to use, and you're going to build a pen next to a straight river. What dimensions should you make a rectangular pen to get the most area? You want your sheep to have as much land to graze on as possible. So in almost every case, what you need to do first is just read it, see if you understand what it's asking. And then we're going to draw it. Just like related rates, we're going to draw this thing and try to keep track of what we're optimizing and what our variables are. So there's a river. And we're building some kind of a pen next to this river. So something like this. Importantly, this pen is a rectangle. This is my grass in here for my sheep. Here, we'll put a little happy sheep in there. That's my fluffy sheep. He's happy. Okay. Now, if it wasn't for this river giving us a free side, the answer would be a square. Right? A square is going to use the least amount of perimeter for the maximum area. But we've got a free side, and so we want to use that to our advantage, and so we expect to get some kind of a rectangle out. We want to now think about what are we optimizing and what are the important variables along the way. So it seems like we want to optimize area. In other words, we want to find the most area possible. In this case, it's a rectangle, so I need a formula for the area of this rectangle. So however you want to write that, base times height, length times width, whatever makes you happy. Let's go with base times height, b and h. So I should probably label that. Every new variable, let's go ahead and label it on here. And I'm going to label this one too. Okay. So now I want to find what b and h will give me the maximum area. But in almost every case in this section, we also got to keep track of our constraints. Okay. So we have this one particular constraint, which is that we only have 1,600 meters of fencing. If we didn't have that, we could make this thing as big as we want. But we have 1,600 meters of fencing, and so we are going to write that down as well. Something equals 1,600 meters. So the perimeter equals 1,600. Okay, well, I would like a formula for the perimeter. So I think I could write that as 1,600 Normally, it would be 2b plus 2h for a rectangle, but one of these sides is free, so this looks like it's going to be 2b. Oh my gosh, I just realized. Forgive me that my height is sideways, but well, let's work with it. 2b plus h. Normally, height would be on the sides, right? So do 2b plus 1h. You can call them x's and y's if you want to. It'll be a good experience for you, me mixing up these usual labels. Okay, so I've got this extra constraint. Why does that matter? One, we need to incorporate it, otherwise this thing could be as big as we want. Second, notice if I wanted to take the derivative here, I have area as a function of two different variables. And we want, really, if possible, to get a function of one variable. So what I'm going to do here is I'm going to write 1600 minus 2b is equal to h. Why is that important? Well, it's going to help us out. We need to take that into consideration to make sure we don't get a ridiculous answer that has infinite size, but we can also use that to plug back in. Okay, so a is equal to b times, and instead of h, we're going to write 1600 minus 2b. Now a is a function of just b, of just one variable. Before we go any further, let's go ahead and multiply this out. A is equal to 1600 b minus 2b squared. Why did I do that? I know I'm about to take the derivative. My next step is to find the max. And that's going to be a little easier if I multiply it out. So if I take the derivative a prime, or if you like dA dB, is equal to 1600 minus 4b. Okay. Fermat says, look for where the derivative is 0. This is my derivative. Let's set it equal to 0. That is 0 equals 1600 minus 4b. If I solve this out for b, I would get negative 1600 over negative 4. b is equal to 400. Very cool. Great, that's where the max is. At this point, we should probably stop and say, what am I actually being asked to do? And what I'm asked to do is find the dimensions. What dimensions? And so dimensions in this case is going to mean my b and my h. So we're almost done. Let's go ahead and find h. H is equal to, well, h is right here. So h is going to be 1600 minus 2 times, well, I know what b is now, 400. That is going to be 1600 minus 2 times 400 is equal to 1600 minus 800 is equal to 800. Great. In other words, my pen should be 400 by 800, which kind of makes sense, right? That if I get one side for free, I expect it to be longer along the top, right? To take advantage of this free side here. All right, let's recap what just happened. I drew myself a picture, made sure I know what was going on. I wrote an equation for what I'm optimizing, in this case area. I went back and I made sure I labeled the right variables for that. I looked for a constraint, especially because I see that area is dependent on two different variables, base times height, and that constraint in this case was my perimeter constraint, that it needs to add up to 1600. I plugged in that constraint to get it down to one variable. Once I got it down to one variable, it was really just a question of, can I find a max or a min, which was taking the derivative and setting it equal to 0. I should also verify that this critical point I found, right, when b is 400, is in fact a max and not like a min, and that should follow pretty quickly whether or not you want to do lots of first or second derivative tests. It follows quite quickly from the fact that this is a downward facing parabola. So if you know the rough shape, then you should know that it's a max. And oftentimes we'll just rely on that. If we know the rough shape of this function, then we can quickly tell, oh, is it a max or a min? How many do we expect? All right, that is our first example, but not our last. Tune into the next video for another example.